Okay, so in this video I want to talk a little bit about how we analyze algorithms. And algorithm is just a fancy word for a step-by-step process. So that's a word that gets thrown around a lot. Sounds fancy. If you ever watched that show Numbers with the mathematician that solves crime problems, he's always using the word algorithm, that he creates a new algorithm in each episode and is able to crack the case. But really an algorithm is any step-by-step process, and so when you're talking about step-by-step processes, you have a lot of those in math and computer science, so lots of algorithms show up. And one thing that we're interested in is working with algorithms that are as simple as possible. And so what we want to do is have a way to analyze how complex an algorithm is. And so what I'm going to run through briefly is a couple of terms. As you've been reading, you should have come across a definition or explanation of the big O notation. And again, this, depending on which teacher you have or which book you're reading, things are explained a little bit differently. When you talk about the big O notation, I think it makes sense in a computer science context to say that the domain of your functions is the natural numbers. So anything that you would input into your function is just a whole number, 1, 2, 3, so on and so forth. And so with that understanding, the big O notation is basically defined this way. So you've got the value of one function less than or equal to a constant multiple times the value of another function. And this might not be true for all values of x, but it would be true for nearly all values of x. So in other words, there may be a few exceptions, is the easiest way, I think, to explain this. But basically what this is saying is that our function f is bounded above, and, well, it's bounded above by some multiple of g. It's some multiple of g. So bounded above, it just means that that multiple of g is its upper boundary. It kind of makes sense if you think about it. It's always less than or equal to a multiple of this function. And if that is true, then what we write is that f of x equals, and this is the big O of g of x. So I'm gonna work through an example here, then we're going to talk about the omega, right? And then maybe at the end I can wrap this up so we can see what the ultimate point of this is. So let's look at an example. So really what this boils down to is if we can figure out some constant here where this inequality, we know this inequality holds true, then we can write the big O notation. So here we've got a function, and again, I use n to represent natural number. We're going to assume that the only thing that we're plugging into this function is natural numbers, 1, 2, 3, 4, so on and so forth. Right, so can we think of a way to bound this above in other words, so I want to write this inequality, and so I can write anything I want over here as long as it keeps the value of this inequality, as long as I know for sure that what I write is greater than or equal to what is over here. Right, well, if we're talking about the natural numbers, 1, 2, 3, 4, then I would be safe in saying this. Let me write that the other way. Right? If this guy is a natural number, then its values are 1, 2, 3, 4, 5, or something larger. Right? So this must always be true. 1 is the smallest natural number. So if I multiply any of these terms by n, it's going to make the term larger. So what I'm going to think about doing is just adding in another factor of n here. That would make that 2n squared. And adding in another factor of n here. Right? It's got to make the term larger, because, I mean, if I think about it with this term, right now this is 3 times 1. So if I write 3n, well, 3 times 1 has to be less than or equal to 3 times n, because n is always bigger than or equal to 1. And so that same thinking applies to this term and this term. And what I'm going to do is I'm going to make all these terms be n squareds. So actually I'm going to multiply by n squared on this term. I'm going to multiply by n on that term, right? I still made it larger because I multiplied by some positive value n. And then I'm going to leave this one alone. Okay, and the reason I did that is because that transformed these all into like terms. So I've got 6, 7, 8, 9, 10, 11 n squared. And so what I've done is I've created this form of a constant times some other function g, right? So this is my c1, and this is my function g of n. Now, to keep things simple, we're not going to worry about the absolute value. Of course I should be thinking about absolute value, but we're not going to worry about it because I've got functions whose values are always going to be positive, right? These are, if I know this is a natural number and I'm adding terms, then none of these can be negative, right? We're not going to mess around with anything that's too complicated. Right, so what matters here is that I've found the value c1 times some other function g, and so I can write that f of n is big O, because I found that constant, of n squared. Right, that means this function is bounded above by some multiple of n squared. In this case, the multiple was 11. Okay, so let me with that example, let me move on and talk about the omega. And you'll notice that this is just the inequalities facing the other way, right? So the value of this function greater than or equal than some multiple of this function. And again, we're assuming that these inputs are always natural numbers. Right, and again, this may not be true for all values of x, but we know that there might just be a few exceptions. Right, we're not really going to worry about that. I'm just trying to make the definition, I'm trying to not make it be completely in my own words. Right? So this is there just to be safe. And if this inequality is true, then we get to write that f is omega of g of x. Right, and we can do that as long as we can find some constant here, probably not the same constant as in the last definition, some constant where that's true. So let me look at an example. Actually, it's the same function that we looked at above. So what I'm going to try to do is figure out something that this function is always greater than or equal to. Right, so again, on this side of the inequality, I can write anything I want as long as I know for sure that it is less than or equal to what's over here on the left. Well, again, if we think about that, we're keeping this as simple as possible, and we know this term's positive, right, because n is a natural number and it's squared anyway, This term's positive because n is a natural number, 1, 2, 3, 4, so on and so forth. And this is positive 3. Well, one way I could make this expression have a smaller value is if I just start dropping off terms. I mean, think about if you have some positive numbers added together. You certainly decrease the overall value if you drop off 2 of the positive numbers. I've gone from, what that would have been 12, and I got rid of these positive numbers, and now it's just 7. Right, so if I think along those lines, I'm going to drop off these 2 terms, and now 6n squared would have to be less than or equal. Actually, it would be strictly less than. We know that for sure in this case. Right? Would be strictly less than all of these, because it's going to decrease the value for sure when you drop off those positive terms. Right, so anyway, what I've done is I've created an inequality in this form where my constant C2 is 6, and this n squared, same one as I had in the last example, is my function g of n. So I can write that this function is omega of n squared. And so in the first example we said that this kind of meant that our function was bounded above. So in the most general sense, what the omega notation tells us, I should have written this earlier, that a function is bounded below by some multiple of g of x. Right? In this case, bounded below by some multiple of n squared. Some multiple of n squared. Okay, so what we're going to work with, for this material is simple polynomial functions where we know all the terms are positive, just like in these 2 examples, and that will keep all of our mathematics very simple, as simple as we can possibly keep it. So I want to try to bring these ideas together so that we can try to understand what the point of this is, and I'll do that in my next example. So I'm going to cut this video off and we'll pick back up.